objectives. By the end of this lesson, you'll be able to perform distributed processing in MapReduce, understand issues with distributed processing and how MapReduce reduces them, implement MapReduce paradigm, divide and conquer, perform word count program, Hello World of Big Data, distributed processing in MapReduce. Introduction to MapReduce. MapReduce is a programming model that processes and analyzes huge datasets logically into separate clusters. While map sorts the data, reduce segregates the data into logical clusters, thus removing the bad data and retaining necessary information. Why MapReduce? Prior to 2004, huge amounts of data were stored in single servers. If any program ran a query for the data stored in multiple servers, logical integration of the search results and analysis of the data was a nightmare. Not to mention the massive efforts and expenses that were involved. The threat of data loss, challenge of data backup, and reduced scalability resulted in the issue snowballing into a crisis of sorts. To counter this, Google introduced MapReduce in December of 2004, and the analysis of datasets was done in less than 10 minutes rather than 8 to 10 days. Queries could run simultaneously on multiple servers, and search results could be logically integrated and data could be analyzed in real time. The USPs of MapReduce are its fault tolerance and scalability. Let's look at a MapReduce analogy. The MapReduce steps listed here manual vote counting after an election as an analogy. In step 1, each polling booth ballot papers are counted by a teller. This is a pre-MapReduce step called input splitting. In step 2, tellers of all booths count the ballot papers in parallel. As multiple tellers are working on a single job, the execution time will be faster. This is called the map method. In step 3, the ballot count of each booth under the assembly and parliament seat positions is found, and the total count for the candidates is generated. This is known as the reduce method. Thus, map and reduce help to execute the job quicker than an individual counter. The MapReduce analogy. Vote counting is an example to understand the use of MapReduce. The key reason to perform mapping and then reducing is to speed up the job execution of a specific process. This can be done by splitting a process into a number of tasks, thus enabling parallelism. If one person counts all of the ballot papers and waits for others to finish the ballot count, it could take a month to receive the election results. When many people count the ballot papers simultaneously, the results are obtained in 1 or 2 days. This is how MapReduce works. Let's look at a word count example. In this screen, the MapReduce operation is explained using a real-time problem. The job is to perform a word count of the given paragraph on the left. The sentence in input says, "The quick brown fox jumps over a lazy dog," and "A dog is a man's best friend." We will then take this sentence through the corresponding steps of splitting, mapping, shuffling, and reducing. The MapReduce process then begins with the input phase, which refers to providing data for which the MapReduce process is to be performed. The sentence used is as input here. The next step is the splitting phase, which refers to converting a job submitted by the client into a number of tasks. In this example, the job is to split into 2 tasks, one for each sentence. Then the mapping phase refers to generating a key value pair for the input. Since this example is about counting words, the sentence is now split into words by using the substring method to generate words from lines. The mapping phase will ensure that the words generated are each converted into keys, and a default value of 1 is allotted to each key or each word in the sentence. In the next step, the shuffling phase refers to sorting the data based on those keys. As shown on screen, the words sorted into ascending order. The last phase is the reducing phase. In this phase, the data is reduced based on the repeated keys by incrementing the value of each key where there's a duplicate word. The word dog and the letter A are repeated. Therefore, the reducer will delete the key and increase the value depending on the number of occurrences of the key. This is how the MapReduce operation is performed. Map execution phases. Map execution consists of 5 phases: the mapping phase, the partition phase, the shuffle phase, the sort phase, and the reduce phase. The assigned input split is read from HDFS, where a split could be a file block by default. Furthermore, input is parsed into records as key value pairs. The map function is applied to each record to return 0 or more new records. These intermediate outputs are stored in the local file system as a file. They are sorted first by bucket number and then by a key. At the end of the map phase, information is sent to the master node after its completion. In the partition phase, each mapper must determine which reducer will receive each output. For any key, regardless of which mapper instance generated it, the destination partition is the same. So for a single word, that word would always go to the same destination partition. Note that the number of partitions will be equal to the number of reducers. In the shuffle phase, input data is fetched from all map tasks for the portion corresponding to the reduced tasks bucket. In the sort phase, a merge sort of all map outputs occurs in a single run. And finally, in the reduce phase, a user-defined reduce function is applied to the merged run. The arguments are a key and the corresponding list of values. The output is written to a file in HDFS. Map execution in a distributed two-node environment. The mappers on each of the nodes are assigned to each input split a box. Based on the input format, the record reader reads the split as a key value pair. The map function is applied to each record to then return 0 or more new records. These intermediate outputs are stored in the local file system. Thereafter, a partitioner assigns the records to the reducer. In the shuffling phase, the intermediate key value pairs are exchanged by all nodes. The key value pairs are then sorted by applying the key and reduce function. Again, the output is stored in HDFS based on the specified output file format. The essentials of each MapReduce phase are shown on the screen. The job input is specified in key value pairs. Each job consists of 2 stages. First, a user-defined map function is applied to each input record to produce a list of intermediate key value pairs. Second, a user-defined reduce function is called once for each distinct key in the map output. Then, the list of intermediate values associated with that key is passed. The essentials of each MapReduce phase are as follows. First, the number of reduced tasks can be defined by the users. Second, each reduced task is assigned a set or record groups, that is, intermediate records corresponding to a group of keys. Third, for each group, a user-defined reduce function is applied to the recorded values. And 4, the reduced tasks are read from every map task, and each read returns the record groups for that reduced task. Reduce phase cannot start until all mappers have finished processing. So, combining your output is an important step once all the tasks are completed. MapReduce job. A job is a MapReduce program that causes multiple map and reduce functions to run parallelly over the life of the program. Many copies of map and many copies of reduce functions are forked for parallel processing across the input dataset. A task is a map or reduce function executed on a subset of this data. With this understanding of job and task, the application master and node manager functions become easier to comprehend. First, the application master is responsible for the execution of a single application or MapReduce job. It divides the job request into tasks and assigns those tasks to node managers running on one or more slave nodes. The node manager has a number of dynamically created resource containers. The size of a container depends on the amount of resources it contains, such as memory, CPU, disk, and network I/O. It executes map and reduce tasks by launching these containers when instructed to by the MapReduce application master. MapReduce and associated tasks. The map process is an initial step to process individual input records in parallel. The reduce process is all about summating the output with a defined goal as coded in the business logic. The node manager keeps track of individual map tasks and can run in parallel. A map job runs as part of a container execution by node manager on a particular data node within a cluster. The application master keeps track of a MapReduce job. The Hadoop MapReduce job work interaction. Initially, a Hadoop MapReduce job is submitted by a client in the form of an input file or a number of input splits of files, each containing data. The MapReduce application master will then distribute the input split to separate node managers. The MapReduce application master then coordinates with those node managers. The MapReduce application master will now resubmit the task to an alternate node manager if that data node should fail. The resource manager gathers the final output and informs the client of success or failure status. Let's look at the characteristics of MapReduce. MapReduce is designed to handle very large-scale data in the range of petabytes and exabytes. It works well on write once and read many data sets, also known as worm data. MapReduce allows parallelism without mutexes. The map and reduce operations are performed by the same processor. Those operations are provisioned near the data as data locality is preferred. In other words, we will move the application to the data and not the other way around. Commodity hardware and storage is leveraged in MapReduce to keep things cost-effective. And the runtime takes care of splitting and moving data for operations. Some of the real-time uses of MapReduce are as follows. Simple algorithms such as grep, text indexing, and reverse indexing. Such things as data-intensive computing, which would include sorting large and small sets of data, stream data, and structured data. Data mining operations such as Bayesian classification, which you'll study later. And search engine operations such as keyword indexing, ad rendering, and page ranking. Enterprise analytics to ensure the business is operating smoothly and with the best decision-making data available. Gaussian analysis for locating extraterrestrial objects in astronomy, which uses very large data sets. And semantic web and Web 3.0 indexing and operations. We set up the environment for MapReduce development. First, let's ensure that all Hadoop services are live and running. This can be verified in 2 steps. First, use the command jps. As shown, type sudo jps, and then look for all 5 services that you need. Name node, data node, node manager, resource manager, and secondary name node. There may be additional services that are used by a Hadoop cluster, but these are the ones that we require as core services. Next, let's look at uploading big data and small data. The command to upload any data, big or small, from the local file system to HDFS is Hadoop space fs space dash copy from local space, and then the source file address space and the destination file address. Now let's look at the steps of building a MapReduce program. First, determine if the data can be made parallel and solved by using MapReduce. For example, you need to analyze whether the data is write once, read many, or worm-type data in nature. Then design and implement a solution as a mapper and then reducer class within your code. Compile the source code with Hadoop core and package the code as a jar executable. Configure the application job as the number of mapper and reducer tasks and to the number of input and output streams. Then load the data or use it on previously available data and then launch and monitor the job. You can then study the results and repeat any of the previous steps as needed. The Hadoop MapReduce requirements. The user or developer is required to set up the framework with the following parameters: the locations of the job input in the distributed file system, the location of the job output in the distributed file system, the input format to use, the output format to use. Define a class containing the map function, and then a separate class containing the reduce function, which is optional. If a job does not need a reduce function, there is no need to specify a reducer class in your code. The framework will partition the input, schedule, and execute map tasks across the cluster. If requested, it will sort the results of the map task, and it will execute the reduced tasks with the map output. The final output will be moved to the output directory, and the job status then reported to the user. Set of classes. This image shows the set of classes under the user supply and the framework supply. The user supply refers to the set of Java classes and the methods provided to a Java developer for developing Hadoop MapReduce applications. The framework supply refers to defining the workflow of a job, which is followed by all Hadoop services. As shown in the image, the user provides the input location and the input format as required by the program logic. Once the resource manager accepts the input, a specific job is divided into tasks by the application master. Each task is then assigned to an individual node manager. Once the assignment is complete, the node manager will start the map task. It performs shuffling, partitioning, and sorting for individual map outputs. Once the sorting is complete, the reducer starts the merging process. This is also called the reduce task. The final step is collecting the output, which is performed once across all the individual tasks once they're completed. This reduction is based on programming logic. Let's look at MapReduce responsibilities. The basic user or developer responsibilities of MapReduce are 1. Setting up the job, 2. Specifying the input location, and 3. Ensuring that the input is in the expected format and location. The framework responsibilities of MapReduce are distributing jobs among the application master and node manager nodes of the cluster, running the map operation, then performing the shuffling and sorting operations. Next are the optional reducing phases, and finally placing the output in the output directory and informing the user of the job completion status. We create a new project. Let's see how we would create a new project. First, make sure Eclipse is installed on your system. Once it's installed, you can create a new project and add the essential jar files to run a MapReduce program. Then, to create a new project, click the File menu, select New Project, or alternatively, press Ctrl-N to start the wizard of a new Eclipse project. The screen shows the new project and select wizard options for the first step. In step number 2, you would select a Java project from the list. Then click the Next button to continue. Step 3, The newly created project has to have a name. In this case, we'll type the project name as word count and click the Next button to continue. In step number 4 of your new project, you will now include jar files from the Hadoop framework to ensure that the programs locate the dependencies to one location. And in step number 5, you will add the essential jar files. To locate these, go to the Libraries tab and click the Add External Jars button to add the essential jar files. After adding the jar files, click the Finish button to complete the project successfully. Next, we'll check the Hadoop environment to ensure we have MapReduce. It is important to check whether the machine setup can perform MapReduce operations. To verify this, use the example jar files that are deployed by a Hadoop installation. This can be run by running the command shown on the screen. Before executing this command, ensure that the words.txt file resides in the data/first location. In the on-screen example, you see the Hadoop jar command being executed, passing it the Hadoop examples.jar file set, word count, and then data/first/words.txt as the input, and data/first/output as the selected output. Advanced MapReduce. Hadoop MapReduce uses data types to work with user-given mappers and user-given reducers. The data is read from files into the mapper and emitted by mappers to the reducers. The processed data is sent back by the reducers. Data emitted by reducers goes into output files. At every step, data is stored in Java objects. Let's now understand the writable data types in Advanced MapReduce. In the Hadoop environment, all input and output objects across the network must obey the writable interface, which allows Hadoop to read and write data in a serialized form for transmission. Let's look at Hadoop interfaces in some more detail. The interfaces in Hadoop are writable and writable comparable. As you've already seen, a writable interface allows Hadoop to read and write data in a serialized form for transmission. A writable interface consists of two methods, read and write fields. A writable comparable interface extends the writable interface so that the data can be used as a key and not as a value. As shown here, the writable comparable implements two methods, compare to and hashcode. Data types in Hadoop. Data types in Hadoop. The first data type is text. The function of this data type is stored to string data. The writable data type stores integer data. Long writable, as the name suggests, stores long data. Similarly, other data types are float writable for storing float data and double writable for storing double data. There is also Boolean writable and byte writable data types. Null writable is a placeholder when a value is not needed. This illustration here shows a sample data type that you can create on your own. This data type will need you to implement a writable interface. As you can see, writable will define a deserialization or serialization protocol. Every data type in Hadoop is a writable. Writable comparable will define your sort order. All keys must be of this type, but not value. Then, int writable and long writable, and the various concrete classes that you'll define for your different data types. Lastly, sequence files refers to a binary encoded with a sequence of key-value pairs. Input format in MapReduce. MapReduce can specify how its input is to be read by defining an input format. The table lists some of the classes of input formats provided by the Hadoop framework. Let's look at each of them. The first class is key-value text input format, which is used to create a single key-value pair per line. Text input format is used to create a program that considers a key as the line number and a value as the line itself. N-line input format is similar to text input format, except that there are n number of lines that make an input split. Multi-file input format is used to implement an input format that aggregates multiple files sequence file one input format to be implemented. The input file must be a Hadoop sequence file, which contains serialized key-value pairs. Output formats in MapReduce. Now that you've completed the input formats in MapReduce, let's look into the classes for the MapReduce output format. The first class is the default output format, which is text output format. It writes records as lines of text. Each key-value pair is separated by a tab character. This can be customized by using the MapReduce text output format .separator property. The corresponding input format is key-value text input format. Sequence file output format writes sequence files to save on output space. This represents a very compact and compressed version of normal data blocks. Sequence file as binary output format is responsible for writing key-value pairs that are in raw binary format into a sequential file container. And map file output format writes map files as the output. The keys in a map file are added in a specific order. The reducer then emits keys in that sorted order. Multiple text output format writes data to multiple files whose names are derived from the output keys and multiple values. Sequence file output format creates output in multiple files in a compressed form. Let's look at distributed caching. A distributed cache is a Hadoop feature to cache files that are needed by the applications. A distributed cache will help boost efficiency when a map or reduce task needs access to common data. It allows a cluster node to read the imported files from its local file system instead of retrieving the files from other cluster nodes in the environment. It allows both single files and archives such as zip and tar.gz. It copies files only to slave nodes. If there are no slave nodes in the cluster, then distributed cache copies the files to the master node. It allows access to the cached files from mapper or reducer applications to make sure that the current working directory is added into the application path, and allows referencing of the cached files as though they were present in the current working directory, vastly speeding up access. Using distributed cache. Step 1. First, set up the cache by copying the requisite files to the file system as shown here. Here we see a bin/hadoop fs command using a -copy from local of the file lookup.dat to hdfs myapp/lookup.dat. This shows us that there is currently no file or directory of that name. The Hadoop fs copy from local, remember, will take a file from your local file system and place it in the target directory within the HDFS file system. Using distributed cache. Step 2. Set up the application's job conf as shown in the example. In this case, we're setting up a new instance of job by creating a new instance of job conf. We then will call a distributed cache add cache file method and create a new URI specifying the location, in this case myapp lookup.dat with the file name of lookup.dat. In the same way, each of the different commands here shows you creating a cache entry for zip files, jar files, tar files, tgz, and gz files. In step 3 of setting up your distributed cache, you will use the cache files in the mapper or reducer class that you create. Once the private path and configure information is in your program, you simply declare an instance of file called f, specifying the new file along with the parameter of .map.zip/some file in zip.txt. This will map your file into the distributed cache. Joins in MapReduce. Joins are relational constructs that can be used to combine relations. In MapReduce, joins are applicable in situations where you have two or more datasets you want to combine. A join is performed either in the map phase or later on in the reduce phase by taking advantage of the MapReduce sort-merge architecture. The various join patterns available in MapReduce are reduced side join, replicated join, composite join, and Cartesian product. A reduced side join is used for joining two or more large datasets with the same foreign key with any kind of join operation. A replicated join is a map side join that works in situations where one of the datasets is small enough to cache, thus vastly improving its performance. A composite join is a map side join used on very large formatted input datasets, sorted and partitioned by a foreign key. And lastly, a Cartesian product is a map side join where every single record is paired up with another full dataset. This style of join typically takes a significantly longer period of time to execute. A reduced side join works in the following ways. The mapper first prepares for join operations. It takes each input record from every dataset and emits a foreign key record pair. The reducer then performs a join operation where it collects the values of each input group into temporary lists. The temporary lists are then iterated over, and the records from both sets are now joined. A reduced side join should be used in the following conditions. When multiple large datasets are being joined by a foreign key, or when flexibility is needed to execute any join operation, or when a large amount of network bandwidth is available as we'll be moving data across the network, and also when there is no limitation on the size of datasets. The SQL analogy of a reduced side join is given on the screen. In the output of a reduced side join, the number of part files equals the number of reduced tasks. So if you have 10 reduced tasks, you will have 10 separate part files. Replicated joins. A replicated join is a map-only pattern, in other words, does not use the reduce phase, and works as follows. It reads all files from the distributed cache, and then stores them in in-memory lookup tables. The mapper processes each record and joins it with the data stored in memory. There is no data shuffled to the reduce phase. The mapper gives the final output part. This type of join is typically very quick. Replicated joins should be used when all datasets, except for the largest one, can fit into the main memory of each map task that is limited by the size of your Java virtual machine or JVM heap size. When there is a need for an inner join or a left-outer join, with the large input dataset being the left part of the operation, a SQL analogy of this type of replicated join is given on the screen. In the output of a replicated join, the number of part files equal the number of map tasks. And again, as this is using memory as one side of the join, it is typically much faster. A composite join is a map-only pattern, working in the following ways. All datasets are divided into the same number of partitions. Each partition of dataset is sorted by a foreign key, and all of the foreign keys reside in the associated partition of each dataset. Two values are retrieved from the input tuple associated with each dataset based on the foreign key and the output to the file system. This type of join is typically very lengthy and, depending on the size of your datasets, can run for a very long time. The composite join should be used when all datasets are sufficiently large and when there is a need for an inner join or a full outer join. A SQL analogy of a composite join is displayed on the screen. In the output of a composite join, the number of part files equal the number of map tasks. The Cartesian product. A Cartesian product is a map-only pattern that works in the following ways. Datasets are split into multiple partitions. Each partition is fed to one or more mappers. For example, in the image shown here, split A-1 and split A-2 are fed to 3 mappers each. A record reader will read every record of input splits associated with the mapper. And the mapper simply pairs every record of a dataset with every record of all other datasets. The Cartesian product should be used when there is a need to analyze relationships between all pairs of individual records, and when there are no constraints on the execution time, as these can take a long time. In the output of a Cartesian product, every possible tuple combination from the input records is represented. Key takeaways. You are now able to perform distributed processing in MapReduce. Learn important issues with distributed processing and how MapReduce reduces them. Perform MapReduce paradigm, divide and conquer operations. Implement a word count program, the hello world of big data.